Okay, good morning, everyone. Today is January 14th, 2017, and welcome to our science chat. And so just as a reminder for etiquette, if you have a video, when you would like to speak, please put up your video, but otherwise, if you're not speaking, please turn off your video. And if you have a headphone, please use that. Okay, so this morning, I think we're going to start off with Hans Lewin. He wants to explain to us something about on his website. So I'm going to share his page here, and I'll let Hans talk about what he would like to do.
Yeah, I want to talk a bit about an image, e-message that I sent to Franklin about what we discussed last time. That was how elementary particles, in fact, how mass is exhibiting itself in physical reality. We spoke about fields, we spoke about ether, and we spoke about how particles should be constructed, and some people said they are hard balls, others said, well, no, they have some structure. And well, what I do is I derived a purely mathematical model. And I started that from a foundation that was discovered about 80 years ago, 81 years ago, since last year it was 80 years, by Gerrit Birkhoff and John von Neumann. And they called that discovery quantum logic. It's a relational structure, and it is relatively simple. It is not too difficult. You can specify it like classical logic. You can specify it in about 25 axioms. So it is an axiomatic foundation. And that's used by some scientists that are more mathematicians than physicists, I would say, like von Neumann. And they showed that the Hilbert space, the separable Hilbert space, is a realization of that foundation. So this Hilbert space emerges from that foundation. And if you explore this further, then you can build a complete mathematical model from something that physical reality and mathematics might have in common. That's this foundation. Physical reality might have that same structure as a built-in structure. And then it follows directly that also that Hilbert space must be a structure that can be found in physical reality. If you explore that further, then you can use many of the mathematical methods that are used in physics also as if it were tools of physical reality. That's what I explored. I have explored a mathematical model that explored the lower levels of physical reality. Most of physics does it from the other side. They do some experiments and look what is going on in inside physical reality, what's observable. But if you do it the other way around, then you get what I did. And so for me, I can derive how elementary particles are constructed inside this mathematical model. There's no other choice than this kind of solution. And for example, an elementary particle such as an electron is nothing else than a swarm of locations. In fact, the electron is hopping around in a hopping path, in a stochastic hopping path, that after a while forms a location swarm. And that location swarm has a location density distribution. That location density distribution is has a direct relation with the wave function of the electron, of the elementary particle. So you can do all kind of mathematics on that thing inside this separable Hilbert space. And that's what I explored. I tried to build relations between functions, Hilbert spaces, and these pure mathematical objects.
Now, what do you mean by the Hilbert spaces? I think people are not familiar with that.
And Hilbert space is a vector space, but not three-dimensional or four-dimensional. It can have infinite. A separable Hilbert space can have an infinite number of dimensions, a countable infinity. And a very important aspect of Hilbert space is that any pair of Hilbert vectors has an inner product. An inner product is also known in between vectors, is also known for mathematics. If you take the outer product or the inner product of two three-dimensional vectors, you get a similar thing, but in the vector in normal three-dimensional vector space, you have 3 dimensions, and there you have an infinite. It can have an infinite number of dimensions. You can also have a finite number of dimensions, but this inner product plays a very important role, and it is proven that you have several choices for the numbers that you can use for specifying that inner product. You can use real numbers, you can use complex numbers, and you can use quaternions. But for example, you cannot use octions or cedions. So the higher dimension numbers, higher than 4, you can no longer use, because what you need is a number system that has an inverse for every non-zero member. That's a criterion that must be served in the Hilbert space. So you can in fact only use 3 number systems to do your mathematics in the separable Hilbert space. If you apply that and you take the quaternionic Hilbert space, that's the most complicated one, then you can very easily build a dynamic model of the universe. You take the separable Hilbert space, you take an operator in it that uses the quaternionic number system as its eigenspace, then you can use that operator to generate a kind of parameter spaces. I'm sorry, my Dutch is my native language. If you do that, then you can take out a subspace that have the same real parts of the eigenvalues. And you use that real part as a progression value, as a time value. And the other part of the eigenvalue you can use as a spatial value, so as a location. So you get locations with the timestamp as eigenvalue of this operator. If you take that subspace that has eigenvalues, it corresponds to eigenvalues that all have the same real part, so the same progression value, the same time value, then you have a kind of vein that can scan over this whole Hilbert space. This vein then creates for you a complete dynamic model of the universe. What you also can do is use these parameter spaces that are created in the way that I described by selecting a quaternionic number system and use that as eigenspace. You can use that to create functions and use that use that parameter space. And with that function, you can use a new operator that use the same eigenvectors, but use the target value of the function as the new eigenvalues. And in that way, what you get is a kind of field, but a sampled field. It is not a continuous field because as in a separable Hubble space, the finest eigenvalues what you can make are rational quaternionic eigenvalues. So they are all countable still.
Perhaps you should explain what you mean by eigenvalues or eigenspaces. That may not another term that people are not familiar with.
Yeah, in the Hubble space, you can have maps of the Hilbert space on itself. You map a Hilbert vector onto another Hilbert vector into another Hilbert space or in the same Hilbert space. If you do that in the same Hilbert space, then there are vectors that map onto itself, map on the same vector. And if they map on the same vector, you call that an eigenvector of that operator. And the value that is between the image of the vector and the vector itself is the ratio of that is the eigenvalue. So it's the number that comes out of the inner product if you multiply the image of the vector with the vector itself in the inner product. The result of it is the eigenvalue. And for quaternionic Hilbert spaces, this is a quaternion. It's a time-stamped location. You can interpret it as a time-stamped location.
All right. So Hans, let's just take a moment here, and I wanted to ask whether anybody else had any questions about what Hans is trying to explain here right now. Do we have any questions for the audience?
I have a question. Is this related to the work of Maxwell? Because he worked with Quaternions.
He started to yeah. What Maxwell did is he had the differential calculus, and you can do that with scalars and vectors, but you can combine scalars and vectors, a three-dimensional vector and a scalar, into a quaternion, and then you can multiply and divide by the thing, because these two together form a number system. You can do that with quaternions, and that was done by Hamilton, and it's done quite often in the 19th century. But in the beginning of the 20th century, people stopped doing that and started calculating separately with scalars and separately with vectors. And they Gibbs did that. He started the differential geometry calculation methods. So they left quaternionic differential calculus. I don't know why, because quaternionic differential calculus is very compact and can quite well be understood better, I think, than differential geometry.
Einstein's work, well, general theory of relativity is somewhat related to that, isn't it?
General relativity uses the higher order differential calculus, and in fact it is a mixture of coordinate systems and differential geometry. Differential geometry uses the nabla operator quite often. And if you want also to be able to switch between coordinate systems, then you have to use tensor calculus. And that's what Einstein did, because he had to cope with the Lorentz transform. The Lorentz transform enforced him to change between several coordinate systems. And if you want to do several different coordinate systems together with differential calculus, you have to marry with tensor calculus. He was the first to use that in order to do this kind of Maxwell-like differential calculus, but then mixed with coordinate systems. Maxwell could have done that, but Microsoft did the real extension for that.
Oh, one other question I have is Henri Poincaré invented the logical approach to theories called meta theory.
Yeah.
Has the theorems that he has derived for meta theory been applied to this approach that you're looking at?
I don't not know his theories. What I used were results from Gerrit Birkhoff and John von Neumann, and they just start with a kind of lattice theory, and from lattice theory you can then try to find realizations of that kind of lattice theory in topology. And that's what von Neumann and Birkhoff did. They were, in fact, more mathematicians than physicists, but they applied their mathematics to physics in the time that people were developing quantum theory.
I see Cornelius, he had his flag up. Did Cornelius want to say something? Did you have a question? Let's see here. Where is Cornelius? He may have dropped off there. Okay, did anyone else have another question for Hans? No? Okay, well, Hans, so I'd like to get back to your website here. And let's see here. So you said this is your latest paper, Photons.
Yeah, that is about
Photons,
these
jerks, warps.
What I discovered is that the wave equation that is often used to trade fields, because fields are supposed to wave and produce waves, that the wave equation contains quite other solutions than waves, and they appear to play a more important role than waves and to the field equations. What these other solutions do is they are kind of shock waves. I better call them not shock waves, but I should call them shock fronts, and that's what I normally do. Is they appear in all dimensions. They appear as one-dimensional shock fronts, and they appear as spherical shock fronts. The one-dimensional shock fronts.
What are each of these terms you have here in your title of your paper here? Because these are certainly not terms we would normally hear, like jerks and clamps and hops and forms. And so what are these things?
The warps is a name that I gave to the one-dimensional shock fronts, and the clamps are the name that I gave to the three-dimensional, the spherical shock fronts. They are the results of triggers of one-dimensional triggers or three-dimensional triggers, but the three-dimensional triggers are in fact point-like triggers. They are hop landings. While the warps, in fact, are something like if you take a long rope and you give a jerk at the begin of the rope, then you see a bump walk to the end, to the other end. And the bump walks and keeps nearly the same amplitude, and doesn't also change its shape very much. You see some artists sometimes do that with how do you call it, when they train horses or so, they can use their they use a kind of rope to dress the horses, and they give it a jerk, and then the jerk make a hope, and then the travels to the end of the rope. That's
So,
what.
so I'm reading your paragraph here. I'm displaying your introduction. So you say the most fundamental discrete object is a hop, right? Yep. So a hop is more fundamental than an electron or anything else, right? So
the elemental particle, the electrons, are point-like objects, and a point has not so many properties. A point can have a location, it can have a speed, but what these elementary particles do is they hop around, and it's a stochastical hopping path that they walk along in a quite arbitrary way, and after a while they have created a hop landing swarm. So a swarm of hop landing locations, and the hop landing locations form a coherent swarm that has location density distribution, and the location density distribution is very closely related to the wave function.
Can you say like how many hops are contained in an electron? Does that make any sense?
Yeah, I think it's about 10 to the 30.
10 to the
10
30.
to the power of 30. It's in that neighborhood. It is an enormous, huge amount of hops. So these these things, these hop landings, are also very tiny, super tiny things. The hop landings are the spherical fronts, and if you integrate over it, that is a kind of tsunami-like front. And if you integrate over it, it gets the shape of the Green's function of the field. The Green's function is a function that diminishes its amplitude as 1 over r with distance r.
So can you tell us, based on your theory, for example, what is the difference between, say, an electron and a positron in your theory? What makes those things different?
An electron can be interpreted as a positron that travels back in time. It's the same thing, only it has most of its properties inversed. It has the inverse charge, it has the inverse spin, it travels back in time, but for the rest it is about the same thing.
So we're talking time travel. That's a pretty big pill to swallow.
That's what the elementary particles in fact do. They can travel up and down in time.
So if I have a positron in my left hand and a electron in my right, you're saying that the positron is traveling back in time, but clearly it's positron is traveling forward in time, because
Yeah.
I can see it do the same thing that the electron is doing.
Observers see things travel only in one direction.
Yes.
But the creator can draw a parameter space which in which you can go up and down into the real part of the quaternionic parameter space. You can also go in the negative direction of the real part of that parameter space. So you can travel, elementary particles can travel up and down, can travel in positive direction and can travel in negative direction. And they have reflection points, and at the reflection points you get pair production and pair annihilation. Annihilation, sorry.
So how do you explain the attraction between a positron and electron with the positron traveling back in time? I mean, how does traveling back in time create this physical attraction?
The travel doesn't, the charge, the electron and the positron have opposite electron charges, and the electron charges they create an electromagnetic field, an electron field, and it is this electron field that causes the attraction between the electron and the positron. It's the field, not the particles attract each other. It is the field that brings them together, that that creates a force that moves them in the direction of each other.
So how do you see the field working? I mean, the field is one of the most fundamental questions, I think. I mean, a lot of people just postulate that.
No, that's it. In the sorry, in the Hubble space, a field is a very simple thing. It is an eigenspace of an operator. It every separate, every infinite dimensional separable Hubble space has a companion non-separable Hubble space, and in the non-separable Hubble space, operators can have continuums as eigenspaces. So they can have a complete real number system or quaternionic number system as their eigenspace, or they can have the target space of a function as an eigenspace, and then you get a deformed field. That the parameter space is a flat field, and the target space of a function is a deformed field. And you can define operators that have this target space of the function as an eigenspace.
Now I'm looking at your paper here. So you have photons here. Why don't you
Wait a minute, Franklin. What he said is the essence of what he's really getting at. I mean, he just said it to you, and you just sort of blew it off.
Sorry.
He's talking about the duality of the Hilbert space. There is the duality between the discrete topology and the continuous topology. Isn't that what you said?
Well, in fact, there are two kinds of Hilbert spaces, and that is one is a separable Hilbert space.
Which means discrete, right? Discrete, right?
That has it is countable. It is discrete, yes, and it is a countable number.
Wait a minute, hold on. You have a discrete Hilbert space which has a topology which is separable, correct?
Yeah. And
now, dual to that, you have another space which has a continuous topology. Is that correct what you're saying?
That's correct. It is also called a rigged Hilbert space, or it is called a Galvan triple, but these are just other names for the same thing.
Okay, but wait a minute. This, to me, I mean, I've been listening to what you're talking about. This is really how the field and the particles, how you can talk about a field and particles at the same time, because you have a duality between the continuous space and the discrete space, correct?
Yeah, it's slightly more complicated because you can interpret as if the separable Hilbert space is completely embedded in the non-separable Hilbert space.
Okay, but still, that's a
And
bit
then,
of technical mathematics. But
yeah,
what you're doing is you're able to convert between the continuous field and the discrete, which is a particle concept. Isn't that what you're doing here?
yeah, but I'm using both Hilbert spaces, and what happens is that the separable Hilbert space is embedded into its non-separable companion, and this occurs in this vein that I sketched that is scanning as a vein over the whole combination of the two Hilbert spaces, and in this vein um, happens that the discrete particles are embedded into the continuums, and this embedding causes this discontinuities in the fields. So the point-like discrete things.
So what you're saying sounds pretty similar to what Cornelius was talking about last week.
Yeah. He's close, very close to what is happening in my theory.
Okay, thank you. Sorry for interrupting. I just wanted to.
No problem. That. You seem to understand what I'm trying to say.
Yes, I think I do. Yeah, a little bit.
Yeah, I think you definitely understand it better than I am understanding it. I tend to get very quickly lost in mathematical things here.
Well, there's this terminology where he talks about embedding and separable topological space. There's a lot of word terminology that needs to be worked out. You need to, that's obviously a barrier.
Well, the main paper that I'm talking about is about 160 pages, and it contains all the theory that is necessary to understand it. But you need to know about something about number systems. You need to know something about Hilbert spaces. You need to know something about differential field I call it.
Yeah, there seem to be a lot of prerequisites to understanding your theory here, and unfortunately, it does tend to be a barrier.
You have to know, a little bit of mathematics, not too much of it. You can understand it after I think a few weeks of study. You have everything what you need. You have captured. I think you need to understand a little bit about differential geometry and things like that. What Maxwell did, Maxwell equations. I use quaternionic differential equations that are very close to Maxwell equations. It's not the same, but they are very close.
Yeah, well, I like to bring the discussion back towards like physical things. So I noticed that you have a whole section here on photons. And I think you make a very strong statement here, which is that the physical community has a wrong idea about the nature of photons. Photons are not waves. They cannot be waves because in free space, waves tend to spread in all directions.
Yeah.
So, but I think most people think photons are in fact waves. So,
no, photons, at least those photons that are able to travel billions of light years and then are still detectable, those photons cannot be waves. Waves cannot do this. Photons, these shock fronts, the one-dimensional shock fronts, keep their amplitude. So they keep their integrity. Even if they travel billions of light years, they stay the same thing. But these things are one-shots. They don't have a frequency. A warp is just a front that walks over a huge distance, but it is a bump that travels and it's just a single thing. If you want to give it a frequency, you must make a string of these things, and you have to spit them out at equidistant instants, so that you get the frequency of these things, and that's why they look a little bit like waves, because they both have a frequency, but the waves fade away very quickly. They lose their amplitude in a very short period and over a rather short distance. But these one-dimensional fronts don't lose their amplitude. They keep going over huge distances and can still be detected. But they are strings of warps. Warps are these separate single-shot shock fronts.
Well, I think that's a very interesting observation that, starlight travels like, millions of light years to reach our eyes here on Earth. And we commonly think of electromagnetic waves as decreasing as 1 over r squared. But I can take my little laser pointer and I can point it at my wall, and I can walk away, and seemingly the brightness of that spot on the wall does not change.
Yeah.
It's seemingly define 1 over r squared, right?
The photons keep their amplitude. They do not diminish. What happens if you are using light waves, the normal light waves, is that you are not shooting just a single light ray. You're shooting away quite a bunch of light rays in all kinds of directions, and each of these rays do not lose their amplitude, but they spread out in several different directions. So a single photon keeps its energy. As one single warp carries 1 unit of energy. One single clamp, that is the spherical front, carries a unit of mass. And at particle creation and particle annihilation, these two things exchange in each other. They exchange energy into mass. 1 unit of energy changes in 1 unit of mass. These are the really fundamental things.
Yeah, I was wondering, has anyone else, noticed this thing with like lasers, that they don't appear to drop off in intensity as 1 over r squared? The light seems to have this special properties. I was wondering, does that disturb anyone, that lasers seem to have this property?
Misconception, Franklin. That's
Pardon?
a misconception.
Is it?
If I understand what you're talking about.
Yes.
If I understand what you're talking about. If you read books on lasers, you'll see that they're basically a focused antenna. They work the same as an antenna.
But but as you increase the distance, like, now maybe I just don't do a very scientific.
Franklin, hold on. What you have is an antenna. An antenna forms a beam, okay? A beam of radiation that goes in one direction. So when you have like a small antenna, like a TV antenna, these Yagi antennas, and then you have these big dish antennas, okay? And they form narrow beams of radiation in one particular direction. A laser beam, because the frequency of the light wave is so high, forms a very, very, very narrow beam. So you're kind of, and if you look at books on lasers and coherent and that sort of thing, you'll see they talk about that.
Yeah, but we know about that. But I think Hans' point is that the photon emitted by the laser doesn't actually decrease in intensity when it hits its target, which is a very, I don't know, unwave-like property.
You have radio waves, electromagnetic waves, that behaves really as the waves that go in all directions, and they are in fact spherical waves rather than flat waves. Photons are not even flat waves; they are one-dimensional objects.
So when does what wavelength does a photon change from a particle into a wave, a radio wave?
I think they are two different things. I think you can use electromagnetic waves to very short frequencies, and because this is just the electromagnetic waves and the gravitational waves, then the photon is, to my opinion, those photons that can travel billions of light years are gravitational waves and not electromagnetic waves, because also the electrical field needs electrical charges in the neighborhood, and in free space there are not these electrical charges that can provide the electrical field. So what they need a carrier field to travel, and what the carrier field can be is just the gravitational field, of what we call the gravitational field. In fact, the gravitational field is our living space where we're living. That is also a field. It's a deformable a thing that some call it ether. I rather call it field. It is in fact no longer that flat parameter space. It's the target space of a function. That field. That field is always and everywhere present. This gravitational field. And that doesn't hold for the electromagnetic field. There are two completely fundamentally different fields.
I have a
I'm
question.
reading this. I have on the screen here your section elementary particles, and this is where you seem to be talking about the gravitational field as a carrying field.
Yeah.
Did someone else have a comment?
I have a question. In Maxwell's work in electrodynamics, he found two types of electromagnetic fields. One was transverse, and the other one wasn't named by him, but we call it the longitudinal field.
Yeah.
Do you have both of those types of fields? Because we can detect them experimentally. You have both of those in your theory.
There is no difference in behavior between the gravitational field and the electrical field with respect to their dynamics in free space. They only differ in the way they react on the artifacts that cause are in fact the sources of the field. The sources of the field for the gravitational field are the hubs, these what I call clamps, the spherical shock fronts. They cause deformation of the field because it is a recurrent process. It keeps going on, and renewing itself, and that's why the field gets deformed. The electrical field is different. It's related to the ordering of the parameter space in which the particles live. The electrical charges are related to symmetries that are different between different versions of the quaternionic number systems. Quaternionic number systems exist in about 16 independent versions, and if you skip off the real value, if you only look at the imaginary part, so the spatial part, then you have 8 different symmetry versions. And if you have a background parameter space and another parameter space, and you look at the symmetry difference, then you can find out that you have the number of different electrical charges that are contained in the standard model. The standard model has electrical charges of +1, -1, 1/3, 2/3, -1/3, and -2/3. These electrical charges, as you multiply them by 3, then you immediately can see that this is directly related with the symmetry differences between the background parameter space and a floating parameter space that's on top of this, floating on top of this background parameter space. So electrical charges and also the charges of the color charges of quarks are directly related to the symmetries of these different versions of the quaternionic number systems that are existing, and they can coexist in the same Hubble space.
One criticism that people have of the standard model is that it has, there are multiple versions of it, but it has between 19 and 29 adjustable constants representing unknown, still unknown physics. Is that type of criticism valid for the work that you're doing, or is it different?
Now, the electrical charges are directly related to the versions of the number systems that exist. With the Quaternions, you have a rich number of different symmetries that are possible to exist together, especially in the Hubble space.
Let me stop you here. You're talking about Quaternions now?
Yeah.
Okay. I mean, I don't think people know what a Quaternion is.
Yeah. The simplest thing to say is that...
Hold on. Let me just, when you said you've been using the term number systems, different number systems, did I hear that correctly?
Yeah.
Okay, I guess basically most people probably don't understand what you mean when you say that.
Oh, you have real numbers, you have complex numbers,
right?
That doubles the dimension. Then
and you have Quaternions.
And if you double the dimension of complex numbers, you get Quaternions.
Correct.
And if you go one step higher, that you double again, then you have the octonions.
Okay.
If you
I don't
go
think
one
many
step,
people, I don't think a lot of people really understand that, what you're just talking about here. I mean, once you get beyond Quaternions, you kind of lost me. But anyway, I just wanted to make that point that you're using terminology a lot of people probably don't understand.
Yeah, it's it is a four-dimensional number system. In fact, it is a 1 + 3 dimensional number system. It has one dimensional real part and it has a three-dimensional imaginary part. And the three-dimensional imaginary part can also be interpreted as a spatial vector, as a three-dimensional spatial vector. And if you combine these in the proper way, then you can multiply these things, you can add them, you can devise, you can use them as a complete number system. That was the big discovery by Rowan Hamilton in halfway the 19th century, that he discovered this new number system.
All right. So I've got the link to Hans's website here. So I think that he's got a lot of interesting stuff, but like we've discussed, you might have to do some homework to learn some of the terminology that he's got in his paper. But right now I want to take a little break, and I want to have David Hilster, who is one of our organizers here at CNPS. He has some things he would like to share with the group. Go ahead,
Okay,
David.
yeah, could you put up the other slide first?
Okay, what slide we got? The here, this one?
Yeah, that would be good.
All right.
I think I have control over it. Hi everybody. If you want to put me up there at the top, or I think I can do that, can I? Plus, there we go. There we go. Hi everybody, Dave D. Hilster, and you know, I appreciate Franklin again. Thank you so much for doing all these video conferences. They started actually 2008, almost 10 years ago. I started them on a dim system, and then it moved further forward in a different system. And I think who took over those video conferences for a long time was Greg Volk. And then now we have Franklin, who's been very kind to take this over and has been doing a great job. Really appreciate it. I'm sorry I don't make the meetings too much, but my schedule and things here at home don't allow me to do that. But I want to thank everybody for continuing to participate in the CNPS. We got a lot of great things going. Hopefully we have Duncan Shaw is going to be doing a report, but I'll go to the next slide here. Can I? Oh, I can't move it.
Yeah,
Franklin,
okay.
Go ahead. Okay, so this is the only slide I have, and then I have a poster here. But right now, 2017, what are we doing? Vancouver, Canada looks like where we're going to be having hopefully having our conference. Duncan Shaw is here today. He met with the university, I believe, on the 11th, so just a couple of days ago. I have absolutely not heard from him, so I don't know what went on, but I did take a look at it. It's an incredibly beautiful location, number one. Number two, it looks very reasonable in price, which seems to be good, but of course I don't know all the details that actually, they have a lot of good stuff online, but I'm sure Duncan, who I'll have talk with you guys about that. I've been working probably 15 years to try to get Dr. James Maxlow as a special guest. If you don't know who he is the premier geologist in expansion tectonics in the world. He lives in Australia, doesn't travel much, doesn't usually travel without his wife, and it's far away. Being on the West Coast, it's a lot closer than on the East Coast, so that's why I looked into it, and I actually got him to commit to coming. The CNPS will pay his airfare. It's not that unreasonable. We do have a little bit of money in the bank, and so to get him at our conference is a huge thing. There's a lot of expansionists in our group, and I think having the premier person there. We also, in line with that, I thought really it comes down to Lifetime Achievement Awards. We have lists and lists and lists of people, but it doesn't help if the person can't be at the conference. So it really comes down to who's going to be at the conference and trying to pick something. And Dr. Glenn Borkert, who is also on the West Coast, who's writing a new book Glenn Borchertz has great influence on a lot of people in the CNPS, and over the years, I consider him to be one of the best philosophers in the group. And he's also, turns out he's a geologist, which is pretty interesting. He said there's overwhelming evidence for expansion tectonics, but he makes a living looking at subduction. In fact, I just asked Dr. James Maxlow on the about subduction and what's happening there. So that would be an interesting duel. I'm trying to get some type of thing where they would actually be on stage answering questions to each other, because Glenn Borchert is obviously extremely intelligent guy, makes a living at geology. A lot of his analyzing the geology is subduction. Expansionists say there's not very much subduction, but the truth is there isn't very much subduction. There's not enough subductions on the world to take all the expansion into account. But regardless, all this means is that I found that it would be interesting for us to perhaps give them, Dr. James Maxlow is, if you don't know a little bit about him, he was the foremost expansionist was Dr. Samuel Warren Carey. He was also Australian, and Samuel Warren Carey was actually very well respected in plate tectonics, but his expansion part was looked at him as sort of a little bit crazy, somewhat like Ron Hatch, who has over 30 patents in the area of GPS, but says relativity doesn't work. And they sort of just ignore that part. Well, in 1994, Carey, before he passed on, he had literally wrote Dr. James Maxlow and said, hey, I want you to take the baton on for expansion tectonics. And of course, expansion tectonics wasn't accepted, as is still not accepted, but Dr. James Maxlow actually didn't want to accept the baton because he didn't believe it was necessarily true. That only happened when he started plotting the South Pole, and the South Pole fit perfectly onto an expanding Earth. That's why I asked him, I said, what was the turning point for him? And now, of course, he is the premier geologist on the planet for this. So to have him as our keynote speaker, if you could, Franklin, if you can put up that poster for us. Okay, this is assuming we're going to go to this place. This is just to let you know that these are our plans. Duncan will be giving us, maybe he'll come to me and says, forget it. But actually, the picture at the top of this poster is the location of the campus. That's how beautiful it is. We have it as July 2017. We don't have the dates down. You can see at the bottom, I have some really nice photos from James Maxlow there and Dr. Glenn Borchert. We would give them Lifetime Achievement Awards. They're both geologists, but one for philosophy and the other one for geology. And expansion tectonics is actually coined by Dr. James Maxlow. And I think there's a couple of things that we could talk. Its implications, he actually came to us, probably 7 years ago, and I gave a talk for him in Albuquerque, because he says, David, I need help because we have geological evidence that there's mass increase. It's not only that the Earth is expanding, but there's mass increase. One of the things I haven't really had him explain to me very clearly is the what that evidence is. So there's a lot of things he can talk about that directly affect. In fact, he now has been working and talking with scientists about a mass from the sun coming in the form of solar winds that is actually coming in at the poles and parts of atoms and then recombining inside the Earth. Actually, my dad and I's book, we're working on our second version of our book, actually has an explanation. I did a paper on that. So he has a lot to say more than just geology itself, because there's huge physical implications to the expanding Earth, and of course expanding Moon, expanding Ganymedes, expanding, and all the other planets. We've had actually another person who's gotten an award in that, which is Alex Scarborough. Unfortunately, he just passed away a few years ago, but he was a huge proponent. And so there's a lot of great things there, and to have him be able to actually come, it's not going to be we have the money to bring him. It isn't that much, and to have somebody with that name is just fantastic. So this is our plans for 2017. We'll hear, let's see, Duncan Shaw, are you around here? Or did he, are you here?
Yes, I am.
Okay, could you put your video and we'll get you up there. Could you talk about the meeting you had with um, the university? You had it this week, correct?
I had it yesterday.
Oh, okay. That's pretty fresh off the. I haven't heard anything, folks. So he may say, "Throw this away. We're going somewhere else." But go ahead, Duncan. The floor is yours.
Okay, I will start with the expression "do not throw it away." It's a nice setting. The University of British Columbia, or UBC, as it's known here. There's been a tremendous expansion at UBC, new buildings, new residences going up all the time as the population of the university has increased. The meeting that I had yesterday involved seeing the accommodation. In other words, the rooms where we can live and take meals as well, and accommodation for the presentation of papers. I liked what I saw. There are two buildings that are interconnected side by side. One takes care of where we live, and the other takes care of where we have our presentations. The rooms that are available for living are extremely nice. There are two categories. One in clusters of four. In between pairs of rooms, there is an area to get together for the people who occupy those rooms. There's a kitchenette, a living room area, TV, and then at the far ends, there are these two pairs of rooms. Between them, there is a bathroom, so that for every two rooms, there is a bathroom. The price for staying there is $69 plus tax, which isn't that monstrous. But the $69 is Canadian funds.
Oh.
And there's about a 25%, roughly, give or take, advantage for Americans coming into Canada and staying there. So there are those rooms, and then there is another kind of room in the same building where there is a double bed, a sitting area, a bathroom, and here for those who would like a little more privacy, the cost is 135 Canadian a day for those particular rooms. In the higher priced rooms, there's a double bed, and in the lower priced rooms, there are single beds. The cost of meals, if we book ahead of time, we can get meals at a cost of $28.50 plus some tax, around $30 per day, breakfast, lunch, and dinner. And I went to the cafeteria in which these meals are offered and had lunch there yesterday. It's a nice place, a very large cafeteria, and they got a fair-sized summer group of students. So
Is that Duncan? Is that functional during the summer? Because obviously we're going to be during off times.
It is functional during the summer.
Oh, okay, great.
The answer is yes to your question.
All right.
Okay. There's parking available very close by, about 2 minutes walk. The parking cost is about $11 per day.
Okay.
For those who wish to bring their cars. There are meeting rooms that will accommodate anywhere from, depending on the room, there's a choice of 3, but anywhere from about 20 up to 55.
Oh, okay. That's a good.
So it gives us a lot of flexibility as to the turnout. And I've seen that the tables in these rooms, they are all on wheels. We can set those rooms up as we want them.
Nice.
And of course there's the was going to say TV, but they're screens, and so those who are making presentations and who want to have stuff on screen, that is available in those rooms. There is if we're going to have a final dinner, there is a much larger room there. It's too big for our purposes. The final dinner, we'd have to sort that one out, David. You and I have to talk about it, or you and the woman who is our go-between here.
Okay.
But they can arrange a final dinner of sorts. But we need to sort out price.
Sure.
Vancouver Airport, it's roughly 20 minutes drive from Vancouver Airport to UBC.
Right.
Somewhere during the conference, if we have it, my wife and I would like to invite those who attend the conference over to our home for a drink, and I'll call it a nibble, but you would get enough food and will work for dinner.
That would be great. That would be wonderful. Our social night, you usually like to have one of those. Yeah.
Okay. Well, the buildings, by the way, these two buildings are roughly 2 years old.
Oh my goodness.
Everything in them is up to date and modern. Their kitchen facilities in the $135 rooms, their kitchen facilities in the $69 room plus sitting areas. So, that seems to be looked after. Now, at this point, what needs to be decided is when.
Right.
And there are two sets of dates that they can accommodate us.
Okay.
And those dates are July 26 to 29.
Okay.
And July 19 to 22.
Okay. That's just right. Exactly where we're needing it.
Okay. And they need to know within about a week.
We can do that. We can do that.
Okay. Good. So if
we can, if they need a deposit or something like that, normally you reserve it, but they don't require a deposit for a little bit of time. Is that correct? Or
but they were a little vague on when the deposit is needed, but not on whether it's needed. It's a 5% deposit on what we order from them.
Okay, that's not bad. We could do that. You can let them know. We will absolutely have that answer within a week.
Well, then, from my end, what is needed by you, David, or the directors is when. And if you can do that, I can get things rolling here to get this in place. The UBC campus is it's a very interesting place. There's a lot of stuff to do on it. Right. There are restaurants around that are not that far away. But if we're looking at most of us breakfasting, lunching, and dining together,
that's fantastic.
There is really quite amazing.
I will tell you, this could become the West Coast of Maryland, because Maryland's a very good central spot. In fact, the MPA met on the East Coast at University of Connecticut because Eberly Spencer was there. But I can see us coming back here quite often. I mean, the prices are great. It's a beautiful place. It's not too hot, obviously, during the summer months, but this is just fantastic. Yeah, we'll offline talk about this. We have a holiday here on Monday, but we'll talk about it. And yes, we can choose a date. That's going to be the most important thing, is to choose a date. I will check with I'll check with our main people. I know Glenn said maybe he would be able to come. I will check with James Maxlow on his schedule, make sure that we don't pick a time that would just conflict with something that he couldn't come. So I think those are going to probably be the tail that wags the dog, I think. So, well, that's great. I mean, is it as beautiful as these pictures? Or are they enhanced?
Well, every place you go has beauty spots and other spots as well.
But it is on this end of this peninsula, sort of. Is that true?
It definitely is on the end of a peninsula, and there's quite a history involved in it. And But my parents went to a long time ago, around 1914 to 18 range, and there's quite a history. But very definitely, it's a promontory that marks the entrance to Vancouver Harbor, which is a
Right.
very large harbor.
Wow, I bet there's some nice little walks around there too. I think,
There are.
I mean, I totally walked around the neighborhood. I saw where you live, Duncan, and I walked around the neighborhoods because on Google you can visit everything ahead of time. So it's just gorgeous. I'm really looking forward. I've never been to Vancouver before, so I am super happy. When I saw what I saw on the web, I was hoping that you would come back with a positive a note on that. So that's great. So we're gonna this week you can let them know. We will finalize it. I'll shoot out emails today to our main participants and make sure that they'll be available. That will also allowing us in picking those dates right away will give everybody else time to plan. I know a lot of people have budgets, so one of the great things is if you buy those airline tickets way ahead of time, things get real cheap real fast. So thank you so much, Duncan. I look forward to the entire conference just because of the place. It's a beautiful place. So thank you so much. Okay, and Franklin, could you put up that other slide again for me? That would be great.
Yep. Do you want the poster or the
no
the meeting one? Okay, this one. Okay.
Okay, so that was the Vancouver. Obviously, that sounds like it's a go for us. We'll be able to put the deposit down. Man, I mean, the place has got absolutely great prices. So a lot of the retirees who are on budgets will be able to have to make it. There's not any excuse there. And like I said, if you buy tickets way ahead of time, today and age, you can go. We've flown out to LA for less than $300 round trip. So, even if you're on the East Coast, you can make it. So let's start spreading the word about that. As soon as we get that date out, I'll put that poster out and we'll start spreading the word and letting everybody know. Let's get as many people as we can. We'll be on the East Coast again in 2018. I already got some people lined up in my mind who will be receiving the awards and things. So, if you have any suggestions or whatever, let me know. But I'd like to talk a little bit about the two other things that I've worked a lot on. For those of you who don't know, I'm pretty much the webmaster for our websites, and we have everything on our own server that we pay for. The MPS pays for. It was on my server many years ago, but that's been all resolved. They pay MPS. CNPS pays for the server. I moved that to a dedicated server. The reason I did that is because I wanted to install Wikipedia, which we'll talk about. The only way to do that correctly, to install that software, you really have to be an IT person. I'm not an IT person, I'm a computer programmer, but I mean, that's simple for me, but we didn't have that type of access, so we're paying a little bit more per year. We pay it in an annum, so that's been moved over. We've been installing it. I've been working really closely with Bruce Nappy, also Nick Percival, but Bruce Nappy is the person who was at our last conference, been really worried about, and I have been, and I've said this, I don't want to beat a dead horse, but I've said it. We have these email chains that get lost in forever, and no one's going to see them, no one's going to use them. So Bruce and I went over and we looked at many forums, and we came up with what we think is a really good software. It's really top-notch software. We've got our spam filters on it because you have to get it up there and let the people try to attack it, because that's all the stupid things. And Bruce has been working with this program at MIT. If we ever want to incorporate that, we may be able to install it, maybe not, but our goal is to move everything over then to a real forum. And move our email chains for that. If you could, Franklin, go to forums.naturalphilosophy.org. Once you get that up there, maybe put that up, and I'll talk a little bit about that. So
forums.naturalphilosophy.org. Okay, let's see if that works.
Okay.
Okay, I think we got that. I'll share that.
Okay. So
There we
great
go.
to have it's great to have a computer person doing this. Man, praise to you here. Okay, so here's what I installed the software here. It's called BB. I can't even remember now. My BB or something like that. It's PHP based. I've installed it. You can see I put a logo at the top. These forums, if you go down, there's ether, expansion tectonics, those kinds of things. There's open questions. There's relativity and special relativity, open questions. These are being put together by Bruce Nappy. He is a really excellent guy. I really like him. He's hell-bent on getting us on here. All of these things are his analysis, believe it or not, of all the email chains going out there. So we also have work groups, which I'll talk about in a little bit. And so this is the forum. You can go there. You can sign up if you want. It's not announced officially because I don't want to announce it until Bruce is ready. But it is there. You can browse around it. The idea, you will have to register for it. But this is a really great BB system. I guess you can cut and paste. His big thing was he wanted to be able to cut and paste from something like Word. It seems to be pretty good at that, but this is a true full blast, full on forums that's ours on our server. And so, and we're getting this ready. It will be announced. We'll have him, in fact, Franklin, we're going to be reserving a day for that. I think we really need to do that because we want to transfer all these amazing discussions to a place where people can see them and search them and all that kind of thing. And I think we have to grow up and do that and bite the bullet and get off of those who don't want to. That's okay, but we need to do that. So I want to really thank Bruce for that, putting this together. And like I said, take a look at it. It's hidden, it's forums. Actually, it's on the front page of our website. You just click on forums. Not really operational because we haven't announced it. So we'll be writing a blog on it. He has to actually have a manual on it. We may actually make a video on our YouTube channel for it, and then also have a Saturday morning dedicated to it. So if you can, Franklin, go back to that slide, that would be great.
Okay. Okay, stop sharing that.
Hey, get your t-shirt, Natural Philosophy. It's actually a nice t-shirt. Okay, we're back there. Let's see, it's sort of funny on mine. Can you move it up or is that just me?
Gee, what is going on with that?
Just do a slide forward and slide back. Look at that. Software people, we know what.
Okay, there it goes.
I can recognize a software bug when I see it. So that new forums organized, we're really blessed to have Bruce Nappy with us. You know, he is just an amazing person. He works with people at MIT, so that's just super. The other one that took me lots of time, and it actually provoked me to move our server. The server we were on was a very simple server, cost only $100 a month. I looked very long and hard at finding a very well-priced, well-positioned, and reputable host, and it was called a web hosting. I don't remember. That's what we were on. They have a sister company, which is the same company for dedicated servers. What that means is you actually have your own computer, whether virtual or not, or real. In today's world, it doesn't matter too much, but we have our own computer on the internet now, and that allowed me to install what's called MediaWiki. MediaWiki is the nonprofit organization and software that's available to everybody on the planet. That's the exact same software as Wikipedia. Now that software isn't simple. It has a lot of plugins, and I spent probably moving the site over and getting Wikipedia and the forums. I spent probably 40 man-hours during the Christmas break on the programming part of it, and I finally got it installed the way I think we should have it. I actually imported the Natural Philosophy database, which was probably 24 hours worth of work. I'm talking about man hours, not one day, but over a number of days. Quite a difficult task because our database is in HTML, and of course Wiki uses its own proprietary language, which if you've ever used an edited wiki is very different. It's not easy to do, but I wrote some custom PHP code suck all those in, and we put in over 13,000 pieces of information on that, and we need to start filling it in, and we'll get to that. If you could, while I'm talking here, go to wiki.naturalphilosophy.org. Again, this naturalphilosophy.org is huge for us because it really gives us a real firm foundation that was purchased in the beginning of our transition to the CNPS. So if you can get to naturalphilosophy.org, Franklin, and put that on the screen when you can, that would be great. And like I said, this Wikipedia is the exact same software. You can see that it looks has the same feel. There's actually themes. I just kept this theme. The introduction here, if you can go up to the top here, go back to the top there. I just want to say something. Don't click around yet. Leave it here. You can see quick links of scientists, books, scientific papers, and organizations. Scientists, books, and scientific papers was an import from our World Science Database. Huge import. And so that, like I said, took many days. I think in all terms, it took me a full week to get that imported. I also did topics with those things. It was not an easy, simple import because for us to index them in the wiki system, there was a lot of thought and a lot of, I blew out the database 3 or 4 times, wiping it out and starting it over again because every time I did it, I saw there was something else to do. But let's click on the scientist links if you could there, the quick links. Again, this is a full-blown wiki. It's the exact same software as Wikipedia. So here you have these scientists and they're all listed. Again, I had to do some custom software modifications to the Wikipedia software to get this to look this way because they don't do it this way. If you go back up to the top, for instance, it took me probably 8 hours just to figure out how to make that index. So if you look at the top there, A, B, C, D, E, F, G, once you go back up to the top there, Franklin. Oh, no, can I do it? Oh, I can't do it. Yeah, I click on, let's see, click on M for me.
M.
And this index that you see there is actually my code, which they don't have in Wikipedia, believe it or not. If you go down then to Max Low, so find James Max Low. Go down.
Max Low.
M-A-X.
Max Low. There
he is. You click on this.
On him.
Right. And so what you see here, actually, the table of contents, the photos, the translation to the actual Wikipedia syntax, which is very strange if you've never seen it. You go further down, you can see his books are there, and you see his videos. I actually went in the database and automatically generated all those kinds of things. So if a person had a book, the book's then linked to them. If you click on Terra Non Firma right at the top there, which is his book, one of his books, right at the books right there. It says books, and there's only one under there. There you go. You click on that, and it'll go to a book. There's his book. These are all generated from the database and linked together. So it was a huge task programmatically to import this into, if you go do a back on this, go back to his page, and go to the top and say view source. It's right up at the top there, right hand side near the search, view source, view history.
Let's see, what did you want to do? Do you want to
view sources? No. Sorry, it's literally a link in Wikipedia, in media link. It's right there. It says read view
right
source.
There, view source.
Yeah.
That one.
The reason you're not. Oh, we make this not open. Okay, here is the format. If you can scroll through that, look at headers are equal, the header and equal. Bold is 2 ticks on each side. So this all had to be translated and put into this format and then imported into the database. It was quite a chore. I had to actually use command lines in Linux to do that. So all those things are done. Now, if you can go back to the very top and go to the home page. Just click onto the home page. Oh no, you don't even need to do that. No, go down, go to the wiki rules on the left-hand side. It's one of the menu items in the site. Okay. All right. This is what I came up with. Why we are closed to the public editing. That's because public editing will require us to become a consensus-based knowledge base, and of course we'll be just pushed out. So that's not allowed. In fact, what's good about Wikimedia is I can make your page. Let's say you want to take care of your page, right? I can make you be the owner or have the ability to edit your own page, your own book, that kind of thing. Those are all controllable. We are going to start work on this and have people working on it. Let's see, another thing, if you can go to main page, so you can read about it there. Again, this is all open, you can look at it, but you can't edit anything. You can create a login, we will have to, okay. The other thing I did was I allowed us to, we had already topics in our database. These topics, every person, every article, those kinds of things had topics. So if you click on expansion tectonics there, what happens here is everything that's related, it had been in our database as linked to expansion tectonics is here. So you'll find people, you'll find books, and you'll also find abstracts. So I actually have every abstract in our database in here. That's over, what, 11,000 abstracts. There are 11,000 abstracts in here. They don't have the content to them. So if you go up to, go up further, go to the home page, go to, well, go up to the search and just search for Hilster, Hilster, and go to my page, Hilster. Okay, just do, okay, there you go, David D. Hilster, click on me. Okay, go down. Okay, all those abstracts and media are put in. If you go to, go to the top, a little higher, the first abstract, they're all listed from in descending order. So the abstract 2016 expansion major objection solved. Can you click on that one, please? Okay, what I have here is only the abstract. I also created a new, what they call info box called scientific paper. Now what I'm going to do is I'm going to be able to go in there and I can put my whole abstract in here. That's going to be up to each person. To automate it from PDF format to this is probably possible. A very hard problem. But what this means is you can, every person can go in there and every abstract they have, we can put that in there. So abstracts are going to be in a wiki. And I tried to put in the latex mathematical, they have a plugin for Wikimedia that supposedly works for functions in latex mode. I could not get that to work, and in fact, everybody I see trying to get it to work hasn't been successful. I will continue to try to get that endeavor to work, but the idea will be is that we have 11,000 abstracts, and we want to start filling in information. Each person who has this wiki, you're welcome now to email me or sign up, and then give me an email, and I'll tell you what you can do to get that. There was one other thing I wanted to show on Wikipedia, if you could, and then then I'll be done.
Let's see here. Where am I? I just temporarily got lost.
No problem. No problem.
Okay. Where do you want to go?
I want to go to main page. And so we're going to be having a session on this itself, just for this, because as an organization, we have to start building a Wikipedia of knowledge the way we see it. So let's go down a little bit on that page. Challenging mainstream. Could you click on the Big Bang, please? Okay. All right. you can throw knives at me, whatever. It doesn't matter right now because it's not the point. The point is here's where we're going to be able to make an impact. When the students of can't remember his name now. A friend of mine, a very good Brazilian friend of mine, who is a professor of engineering in Niterói, which is across from Rio de Janeiro. He teaches his students to take on, if they want to take on something like the Big Bang, then they are required to not only talk about the good stuff about it, but criticisms for it. Now, there's not very much perspective from our perspective, which we have a lot of people, including Glenn Borkert and many others, who can talk about why the Big Bang is not, there is arguments against the Big Bang. So what we want to do as a group here is we want to do is for the wiki is to get ourselves together and start writing these and filling these out with the perspective of being able to have criticisms to the Big Bang and point to papers of those criticisms to the Big Bang and be able to do a wiki the way we would like to try, and we've tried, and many dissidents for at least 15 years have tried and failed miserably. I'll give an example. Go to expansion, you don't need to do this, Franklin, but if you go to Wikipedia and you look up growing Earth, I think it's what it's called, or expanding Earth, they were listing scientists who believe that. I put James Maxlow. James Maxlow is unarguably the top person in there. I put it in. Go look in the history. You'll see where David D. Hilster put in James Maxlow, which is, you don't have to agree with it. They already have other people there. They took it out. And the only reason I can think they took it out is because, not because I was putting somebody there shouldn't be. I was putting the top guy because they don't want the top guy there. And so there is censoring going on there. I'm not into conspiracies, but you know, they're what I call pseudo intellects. They think they know everything. And so this is the place where we can build this Big Bang should be very long. And we should have lots of information, not only about the Big Bang, but criticisms of the Big Bang, who criticizes that thing. We shouldn't come in here and just say it's wrong. We can say these are what's said, but we need to give a student, if a student from high school comes and wants to look at about the Big Bang, they go, I want to go to the natural philosophy people because they have alternatives. I always thought the Big Bang was sort of screwy. What do they say? And so that's what the idea here is, of what we want to be doing. So that's pretty much it. Franklin, like I said, we're going to be setting up a time for the forums and also the Wikipedia on some Saturday early this year. And that will be for us to talk about it. We do have working groups, what I call working groups. We have a working group I'm setting up. If you go to working groups on our webpage, if you go about and hit working groups, you'll see people that I've put in there that are working groups in areas we have to start working on. So one of the things we plan to do is what I call have a producers meeting once every couple months on the Saturday morning. Take the time to do that and talk about how we're doing it, where we are. We have to actively spend time as a group, not only talking about theory, but working on the marketing of that. I know Dr. Lucas is here. He's talked and given us many suggestions, but those suggestions mean nothing if no one's implementing them. I can't do it all myself. Other people can help out. So we have great opportunities with us, and so I thank you all for taking the time to let me barge in here. I'm going to be heading off. I don't know if there's any questions anybody has. You want to raise a flag? I don't know anybody want to chime in. They can ask me whatever questions about the CNPS. I am the president, so you know, if there's something that you want to air out now or ask, you know.
Yeah, are there any questions for David? This is your big chance.
They're afraid of me.
No, but it sounds great. The Vancouver locations.
Oh yeah, it's great for you, huh? It's like how
it's very,
you can
very
drive
short.
to it, huh?
Yeah, I could drive to it. I could bring my RV.
Oh, cool. All right, we'll have parties in his RV.
But I think it's very impressive the work that you've done on the forum. I'll be happy to see if we can actually force all these people who only know how to use reply to all actually to use the forums.
No, it's great to have you, Franklin. I mean, we have several people who are very computer literate. That's not their field. And I will tell you, it's really funny because there were two things that the CNPS, the MPA, then the CNPS went through. Number one was paying online. I was getting conspiracy theories that, everybody was stealing money, that there was some dark organization that they wouldn't want to pay online because they had their names and numbers and all that. We finally got that, and finally it was Don Burdell says, I'm the treasurer, everyone's paying online, no one send me a check. And we finally got over that, and that's good. The second thing that it took forever, believe it or not, was just having the web page and emails. People were wanting news. In the very beginning, I started in the MPA in '96. It was newsletters. They said, "You can send me an email." I don't have an email. I don't want to use an email. I don't use a computer. So now we need to move that over, and I think just pressure. And I think I'm not even sure who's in charge of it, but we need to find the person in charge and just shut it down and say we're moving it. So that's going to be part of that. Bruce Nappy's going to be working on that, and it's going to be so much better because the number one problem I see in those email chains is I get the flack from it. Dave, take me off the email chain. So what happens? You're on the email chain, you want off the email chain. So you tell the person, I want out. The only way that's going to happen is everybody who's going to reply next has to remove you. So what happens? The person who's next removes you. The next person who then replies, if they don't reply to that, they reply to something before that, you're back in again. So there's so many disadvantages to that. So
Yep,
anything
I'm
else?
looking forward to that. All right. Well, let's see here. Looks like we only got about 20 minutes left in our conference.
I will
I
take
was
you off.
wondering, does anybody else have any new subjects they would like to bring up for discussion? So our chat, we are a chat here. So if there's something you'd like to talk about, this is your chance. So does anyone want to do something like that?
I'll see you guys. I'll get myself
All right.
out
Thanks,
of here.
David.
No, thank you.
Now, if not, I've been working on some new things. So if you guys have published any new papers or anything like that, that this is an opportunity for you to describe what your papers are and get some feedback on it. So if no one else has anything new they would like to bring up, I'm going to bring up a new paper that I have, and I normally keep my papers in academia.edu. Okay, let me share that with you guys. All right, if you're not familiar with this site, I think you do actually have to be somehow associated with an educational organization. So it's like I went to MIT, so I kind of use that as my excuse for being in this place. But otherwise, this has kind of been my top place to publish. And apparently I'm the top 2% in this particular website. So so I have all a bunch of papers. So my newest paper is, oh yeah, how protons are attached with neutrons. So the way this website works is that you can click on the title and you can get a preview, but I believe in order to actually download the file, you actually have to register. So that's a little bit of a disadvantage that you have to register and provide some credentials and stuff like that. But I believe that you can just usually click on the title page here. So, but this paper has to do with the question of atomic structure and how the protons in an atom manage to stay together. Since the main problem is that protons repel each other. So mainstream says that the protons are held together by the strong force, which seems to be this completely arbitrarily made up force. So I was wondering out there, are other people disturbed by the strong force? Did it just seem like a totally made up thing?
Franklin Duncan Shaw,
Mm-hmm.
can you hear me?
I can hear you.
I'm with you. I think of the strong force as being very simply the difficulty in breaking apart particles that are physically latched onto each other. And it takes a hell of a lot, say in the nucleus, to break those latched together particles apart. Therefore, it takes a strong force to do it. Therefore, there's a strong force. I don't think there's a strong force at all. I think it's damn difficult to get bound things physically bound that are physically bound together apart.
Yeah, that's true. I mean, it is strong in the sense that you can't tear atoms apart very easily.
Yeah.
But is it this strong force that the mainstream is talking about, which is this kind of weird force, which is super weak when the particles are totally close together? Because when they do experiments, they find that there's three things in a proton, and those three things are actually not strongly bound together. So the strong force is very weak at that level, but it's very strong at the atomic nucleus level because it holds all the protons together, but then we don't see it at all outside the nucleus. So what kind of crazy force is that changes its strength that radically depending on distance? So this whole paper is kind of based on trying to solve that question about how things get glued together. And the thing about the strong force explanation is that it really doesn't explain what the role of the neutrons are, right? It's not really clear. If you had a strong force, you could probably put together protons with no neutrons, because the neutrons really aren't adding anything as far as reducing the repulsive force of the protons, right? They're neutral, so the full force of the protons is still there. So I tried to come up with some kind of geometric argument for how this works. So the idea is that, first of all, we have to redefine what a proton is. And so I thought the easiest thing for a proton to be is just simply two positrons and an electron, right? So that leaves your net +1 charge. So we would start with that. So the question is, if a proton is that, then how would you glue together protons? And the picture I had is that you can just stick an electron between them. So in my paper here, I've diagrammed that you have a proton, an electron, a proton. I mean, positron. Excuse me. A proton is made out of positrons and electrons. So if I misspoke, I don't want to confuse anybody. That you could just glue together two protons by just putting an electron between them, right? So that makes sense. And the atomic nucleus isn't this big giant long chain of protons with electrons between them. They would seem to be kind of a loop. So I have my other picture here where I show the two red circles are the protons, and the positrons. So the two red circles are the positrons, and the black circles are electrons. So what I have here is that the two positrons and electrons, those form a proton. And those are basically glued together by these two electrons. So we can see that we can glue together protons pretty easily with just electrons. So that's the basic idea, except that so the question is, what on earth is a neutron? So we know a neutron is a neutral particle. So at the very least, it has to contain even numbers of positive and negative charges. So I'm thinking that the neutron is just a positron and an electron. So we use the electron from the neutron in our diagram here, which is this big black circle. And we use that to glue together our two protons. So this is why you need neutrons to glue together protons, because you need to use the electron from the neutron to do the gluing. Now, the only thing is that this leaves you with 2 excess positive charges from the neutron. So the way you neutralize that is, well, you just throw another free electron in there. So my other diagram here is showing that you just have the positron, which is the big red circle, and then just another electron, which is not really bound into anything, but it's neutralizing the charges. So that's the basic idea of how you can use a neutron, which is just a positive negative charge, to glue together your protons, which are basically 2 positive and 1 negative charge. So that's the basis. So I'm looking for opinions. What do people think about that?
How does this deal with the strong force?
It gets rid of the strong force. It replaces the strong
Well,
force.
wait a minute. Getting rid of the strong force doesn't gain us anything. Then we can't explain how nucleus holds itself together. So I don't see what's the benefit of getting rid of the strong force.
Well, the benefit of, well, I'm not sure you really understood what I was trying to say, which is that I'm replacing the strong force. You don't need the strong force. You can hold the nucleus together with just electrostatic forces using the geometry.
What are we talking about here? Are we talking about, I heard a couple of different things. One is, it sounded to me like you were talking about gluons or the strong force and holding quarks together. And I'm not sure whether we're talking about that or we're talking about what holds the protons and neutrons in a nucleus together. So I'm not really sure what you mean.
Okay, well, let me see if I can clarify that. So I'm strictly just talking about protons and those consisting of positrons and electrons. There's no gluons. There's nothing like that. There's only the Coulomb electrostatic force.
In which case, a nucleus would fly apart except for the strong force which is holding it together.
No, I would say that the nucleus does not fly apart because there are electrons that are right next to those protons that are neutralizing the positive electrostatic field. So instead of, the conception is that the nucleus only contains positive charges. So the radical new idea I'm introducing here is that the nucleus contains both positive and negative charges in basically a perfectly balanced checkerboard format, just positive, negative, positive, negative, positive, negative. So if you do that, then you can explain why the nucleus stays together without using a strong force. So the trick is you have to put the electrons inside the nucleus.
Well, I guess my question then would be, you're saying that the electrons are binding to the protons and we don't really need neutrons at all.
No, you do need the neutrons. The neutrons.
What do they do?
Because in order to bind together the protons, you need to have that negative charge. And so the neutron provides that negative charge.
So that would make the nucleus neutral then?
Yes, the nucleus is actually neutral. Perfectly neutral. And that makes it easy because then you don't have to deal with this unbalanced charge thing.
Then I could shoot a, you know, that doesn't seem to follow from any of the experimental facts of nuclear physics.
Well, you have to look at what the experimental facts of nuclear physics are.
Well, I mean, that's what I'd like for you to do.
Which is, if you look at Rutherford, I mean, this is the experiment done, you know, like 100 years ago by some grad students, firing alpha particles at gold foil. And, you know, if you just think about that intuitively, it's like, do you really think you can tell something about the subatomic structure in such an experiment? Just intuitively, I think the answer is kind of no, because basically you know, the only thing you can see out of that experiment is the how it scatters things back at various angles. And based on just that very not very much evidence, Rutherford decided that the nucleus must contain all of the positive charges in one spot, because that's the only way that these alpha particles could possibly bounce back if they were being repelled by electrostatic forces. So do you understand, you know, why did they even think that all the positive charges are in the center of the atom?
Well,
I think you have
because
to start
only a
with
very
that.
small portion of the particles that were shot at the foil bounced directly back, and most of them were deflected at small angles. And so the model that they created agreed with the idea that there was a concentrated, hard, small nucleus at the center.
Well, actually, it wasn't a hard, small nucleus. It was more like, in order to get that very high angle reflection, you had to concentrate all of the positive charges at one spot. Now, this is a little bit different than what we would normally consider a collision. Like if I throw a tennis ball at a wall, it bounces back. They actually don't think that the incoming particles actually bounced back from the atomic nucleus. Now, the funny thing is that if you do the same experiment with electrons, now electrons should be attracted to that nucleus, but the thing is that those bounce back just the same, which is telling me that it's not really the electrostatic repulsion that's causing the bounce back. It's just a standard elastic collision. So that basically invalidates the equations and their model that they were using.
Yeah, but apparently nobody's agreeing with that.
No, that's what we do here at the CNPS. We bring up radical new ideas, and this is one of them, because of, you know, I asked the question, is anyone else disturbed with the idea of the strong force? And it just seems ridiculous. So this is an alternative. We instead of doing that, we redesign the atomic nucleus to be assembled by just electrostatic forces, which we understand. So that's the basic idea.
Franklin, Duncan Shaw again. You mentioned, are there any new papers? I will mention one. I've got one in Physics Essays, December 2016, which is entitled Outflowing Ether. It's an aspect of the, I'll call it the hypothesis of the cause of gravity that I've developed in earlier papers. And if anybody wants to see it, it's on my website with the permission of Physics Essays. And my website is www.duncanshaw.ca. And access to that paper and other ones is on that website.
Let's see if I can find your website here. DuncanShaw.ca.
That's right.
Okay, there you go. There's your website.
And you keep on going down, and you will find. Wait a moment. Stop flowing ether, structure of atoms. Maxwell's. One more down.
Oh, that's the bottom here.
Let's go back.
Oh, outflowing ether.
Oh, outflowing ether. There it is. Yeah.
There it is. Okay. Well, if next week we are at the top of the hour here, so we need to conclude this week's conference. But next week, I would invite you to bring this up, and we can talk about it.
Okay, be pleased to.
All right, and it looks like Hans, do you have a closing comment? No?
I wanted
Okay.
to note that I also published a paper in the FQ XI contest. It's a website where you can discuss things about physics, but they also regularly hold how you call it, contests. And I introduced there a paper with the title Intelligent Spaces from First Principles.
Let's see, what is their website? How do you spell that?
FQ
FQ. Oh yeah, these guys.
XI.
So what is their latest contest?
It's about
Wandering towards a goal. How can
yeah,
mindless mathematical laws give rise to aim and intention?
yeah. That's what I tried to show, how you can produce intelligent species starting from mathematics.
Okay. Well, once again, I would invite people, if you've recently published a paper, to bring it up here at Science Chat, and we can talk about it.
I also mentioned this in the chat. Is there a possibility to also store the chat, the content of the chat? Sometimes the chat contains a lot of interesting stuff. Is it available when the conference is saved?
Yeah, the chats are saved. You have to use the direct replay link provided by Fuse.
Ah.
So what I've been trying to do is that David's been moving the conference recordings to YouTube, but that doesn't have the chat or anything like that. But I've been trying to like put the direct link in there as well, so if people want to replay it that way, they
Yeah.
can do that.
Can you describe this in a mail also? How to do that?
Just how to view the
How you can get access to these chat storage place?
like I said, I'll put it in the comments in the YouTube videos. So like
you on the right side, you get a chat column, and
yes.
sometimes there's a lot of interesting stuff in it.
Mm-hmm.
So I like to know how I can access that when the video conference is stored.
Yeah, you need the link, but I have to give it to you.
Yeah, good. Thank you.
I'll try and provide the link with the YouTube video that is normally published.
Good. It's nice.
Do you know how to access? Do you know how to access the? Because all of these conferences are replayed on YouTube.
I know.
And I try and put a comment in with the topics that were discussed, and I'll try and put in the link to the replay.
Thank you.
Okay, so we are at the top of the hour, and that does it for this week's edition of our Science Chat. And just to summarize a little bit about what we've been talking about, first we started out with Hans, and he was explaining about his Hilbert spaces and his hops and his jerks and the various other things that he has. Then we were discussing, we had David de Hilster here, and he was announcing what was going on with the CNPS this year, 2017. One of the most exciting things is that we do have a conference going on, and it sounded like we had a good report about having a conference in Vancouver, British Columbia. So that will be an exciting thing for us to be involved with. And there are also upcoming forums, and there's already an active wiki site, which is wiki.naturalphilosophy.org, that is already up and seems to be populated. So be curious to click around there and explore all the information of people who have participated in the CNPS. And finally, I brought up a new paper of mine about trying to get rid of the strong force by replacing it with just an electrostatic force that glues together the protons using the neutrons. And I invited everyone that if they have some new paper, that we can bring that up as a topic in our next science chat, so we can get some feedback about what people think about these ideas. But that's it for this week, and we will see you next week. All right.